Hey, welcome to Monday. Hi, Verge.
Hey, everybody. Let me turn my video on here if I can. Hey, everybody. Welcome to AP Live with Mark and Verge. Some of you might be here for the first time because, why? Because we're starting to review right now. Right, Mark?
I'm hoping there's a group in Denton tuning in today. I sent out a remind this morning and said, hey, we're starting review limits. Let's get there.
Yeah, my students too. My students need to be taking notes all from now, this moment forward, because these are the review topics. So it's imperative.
All right. I am Mark Corelli from Ryan High School in Denton, Texas.
And I'm Verge Cornelius, and I'm at Lafayette High School in Oxford, Mississippi. And folks in Mississippi got a lot of bad storms yesterday. And in Texas, where Mark is, they had them about 12 hours earlier. Is that right?
That's
Mark?
about right. Yeah, yesterday morning.
So I feel very thankful that we actually have power now, and that I actually have internet right now, because that was not true about 4 hours ago.
Yeah. And we went from 90s last week to 40s this week, so we'll see how it goes.
Yeah.
All right. So we have officially started our review. So this slide got a lot smaller and a lot more crowded at the same time. There's a new bit.ly there, and that QR code takes you to the exact same address. All it does is it takes you to a shared file in our Dropbox folder of this. It's the schedule for the next few weeks up until May 1st. And as Verge said when I put it up there, we're intentionally making it small. You can follow that QR code, and I'll put this slide up again at the end. So where we're headed, this will end May 1st, although I think Verge and I are in talks of continuing another week of review after that now. And then up till May 12th, same time, same station, right? Well, not the same station, but at 2 p.m. Eastern on May 12th, we'll have a 45-minute exam for you guys, and hopefully some college credit will be earned.
So what Mark was saying was that this is actually the 14th day of our AP Live, and we are scheduled to end on May 1st. Well, now we know the exam is May 12th, so we might actually get to go for another week. We'll keep you updated on whether or not we're going to be able to do that. So this is a very fun slide here, daily corrections and oversights. And for each lesson day that we don't make any mistakes, we add a number, kind of like in a factory.
That's right. Yeah,
it feels that way sometimes. We're up to 2 days.
I think 6 was our high. We thought we had 7. And I do want to have a shout out. I just got a text. At least one of my BC kids is here. So hi, JC. All right.
That picture is from 2019 at the AP Calculus reading in Kansas City, when we were not just co-hosts, but co-question leaders. And so we had just finished presenting, or maybe we were just starting. I can't remember.
Yeah, one of the two, right?
Yeah.
All right, so we're done with our introductions and banter. We're about to start our warm-up. It is going to be a lot like last week's, because that was a review section of Unit 8, where we roll right into the lesson, which is limits and continuity today. And then we'll wrap up, let you know what's in the Dropbox. Actually, what you'll see us working on today is already there. So if you're watching this on recording, you can pause, go down to the description, open that up with a little arrow, and click on the Dropbox and get that document if you want. And you'll have to, in Verge, you're gonna have to take it for a second, because I have someone with, I have a 4-year-old with ponies coming up to my table.
All right, well, let's take a look at that warm up. Hey, Mark, let's take a look at the warm up. All right, so here's the warm up. It says, use the following graph of the piecewise function f of x to find the requested values. And then there's 3 questions that we have here. Again, like Mark said, if you look in that shared folder, you'll see a document that is pretty much notes, and you can go ahead and work them along with us. You can print them out, or you can just take a look at them. However you want to do it, but we felt like we wanted to give you guys some notes. So there's this crazy looking function. It is a function. It passes a vertical line test. We are asked to find f of 0. We are asked to find the limit as x approaches 2 from the left of f of x, and we're also asked to find the limit as x approaches 4 of f of x. Now, usually in this part of the lesson, I let people work on this for just a little bit, and I tell a joke. Mark, you ready for a joke?
Yes, I'm sorry. It was my daughter just got out of the bathtub and discovered that her Christmas gift, My Little Ponies, changed color, and she came into the setting. Yeah, so I should have just thrown her on camera for you. It's quite cute.
So
All right.
cute.
So
All right,
yes.
I want to tell you this, Mark.
All
So
right.
you know, math teachers never grow old.
Math, that's good news. So why do math teachers?
They just lose some of their functions.
Ooh.
Speaking of functions, let's take a look at this one.
I'm going to try not to confirm that. I think.
So f of 0, let's see, maybe we can use your cursor, Mark, to kind of show us where f of 0 is.
So 0 is that right? There's my x of 0 right there.
And if we're asked to find f of 0, that would be the y value when x is equal to 0. So that's not going to be 2, it's going to be 1. So the answer there would be 1. The limit as x approaches 0 of f of x would be 2, but f of 0 would be 1. All right, let's go ahead and take a look at the second one there. The limit as x approaches 2 from the left of f of x, and maybe Mark can get his cursor out there again.
Yep, sorry.
That's okay. As we approach 2 from the left. I messed this one up a couple days ago. I actually was approaching -2. So we want to approach +2 from the left. So we need to get on the function on the left-hand side, but pretty close to 2.
Up here.
Oh, very fancy. What happens to our limit? Our limit of our function goes to 4. So that's a one-sided limit. And that value ends up being 4. And then finally, on number 3, the limit as x approaches 4 of f of x.
As x approaches
that
4.
One, since we're not told, sorry, as x approaches 4, that one we're not told
that's
from
not
the left or the right. Oh, weird.
That's actually that should be a 3.
Does that count as a mistake?
If we catch it, I don't think so.
I don't think so either.
Let's see.
So the limit as x approaches 3 of f of x.
It says 3.
Oh, there you go. Very nice. In that case, that's a limit where we need to consider approaching that x value from both sides. So there's Mark's red right there.
I have to get back in here, yeah. I think I'm about to lose this. Hold on.
That's okay. I can share my screen because I have it.
Oh,
you wanted to do that, Mark.
No, I didn't, but it worked out well, didn't it?
I'm going to go ahead and share my screen.
Okay, go ahead and take the document. Yeah, that's fine.
Yep. Okay, so let's go ahead and take a look at this one. And I have the limit as x approaches 3 of f of x. Well, here's the 3 right here, and the origin is right there. So as we approach 3 here from both sides, our limit of f of x is actually 0. The y value is going to 0. Remember, f of 0 is equal to 1. That's right there. The limit as x approached 2 from the left of f of x was equal to 4. That one was right there. And then last one, the answer was 0. So as stated earlier, this is a review on Unit 1. Unit 1 is many, many days, maybe like 3 weeks.
Yeah.
And what we did was we just picked some things to highlight and go over with everyone so that you could start stirring it up for yourself. Are you done? Finished with Unit 1 after today's lesson? Absolutely not. There's way more review that you can do for yourself that your teacher might guide you with, things like that. But for right now, we're going to do some highlights basically from Unit 1. One thing I always do, if you're new, this is going to be new to you, is I always have a little post-it note here that I write every night before I go to bed. I was very confused yesterday morning. I was very confused because I woke up and thought it was Monday, actually, because I had written a post-it note for Sunday, but we all know what these crazy days are. We don't know what's going on. Okay, so as advertised, this is some work on limits. And this next one we're going to do is an algebraic limit or an analytical limit. And we had changed our numbering. So I don't know what number this is, but you all have it. We can call it number 4. It's the limit as x approaches -5 of x plus 5 over x squared minus 25. So instead of having a graph that we're looking at this rational expression here. So some things that students do to try and figure out the limits is they might do what's called direct substitution, where you substitute in -5 to the numerator, figure out what you get, substitute -5 into the denominator, figure out what you get, and then go from there. This one ends up being what's called an indeterminate form, because the limit as x approaches -5 of the numerator ends up being 0. And then the denominator, the limit as x approaches -5 of x squared minus 25, also ends up being 0. So I cannot determine this limit by direct substitution. I need to figure something else out. Now, because we're reviewing, we all know about things like L'Hopital's rule and things like that, but I'm going to pretend like I don't know about that because I didn't know about it at the beginning, right? I didn't know about derivatives or anything. So what might we do here, Mark, to figure this out?
I think so. Maybe some factoring, since I don't want to put any kittens at risk.
Yep. No canceling here, must factor first. So this is equal to the limit as x approaches -5 of x plus 5 over, we've got difference of squares here, x plus 5 times x minus 5. And then these factors cancel. They're equal to 1 as long as x doesn't equal -5. And so I then have this limit equaling 1. I'm going to put it down here. This is a big old mess. 1 divided by, now direct substitution, -5 minus 5, -10. So that limit ends up being -1/10.
That's what I got.
Yay.
That's not always happen. Doesn't always happen that way.
This next one, I guess we could call it example 5.
Yeah, it's 5.
Yeah, this one is the limit as x approaches 3. And yeah, well, our numbering was off when we first did these this notes
but
page.
it's on until the very end that the numbering was off. I don't think.
Okay. Limit as x approaches 3 of another rational type expression. Let's see what happens with direct substitution. 2 times 3 is 6. 6 is 9. Square root of 9 is 3. 3 minus 3 is 0. Divided by 3 minus 3 is 0. So this is another indeterminate form where I need to do something else to figure out this limit. Probably something algebraic. I got a square root. What you thinking, Mark?
Oh, geez. Well, it's kind of related to that denominator in number 4. If I could do some handy conjugate work, that would be pretty cool.
Ooh, so back to algebra 2. When you think about a conjugate, a lot of times it's when you're trying to rationalize a denominator or dealing with an an imaginary number. But here we're going to rationalize the numerator. So square root of 2x plus 3 and then plus 3 is what I'm multiplying numerator and denominator by. And I intentionally set this up strategically because my middle term will cancel in the numerator here when I expand. So I get root 2x plus 3 times root 2x plus 3 is just 2x plus 3. And then -3 times 3 is -9. And then in the denominator here, because I've done about 657 of these in my lifetime, I know to not...
How do you know how to do that so fast? Because I've done a lot of them.
Yeah, well, I know also not to distribute in the denominator because I know I'm setting this up. Yeah, I know that I'm setting this up so that I can cancel somehow with the numerator. And indeed I can. 3 minus 9 is -6. And then I can factor out 2 because I have 2x minus 6 is the same as 2 times x minus 3. And this is still my limit as x approaches 3. I'm just trying to do some algebra to kind of massage this and get it to where I can do a direct substitution that'll work. I think now I can. This is equal to 2 divided by the square root of 2 times 3 is, well, I already did that, didn't I?
Yeah.
I think I did that, right? So I end up with 1/3. It's 2/6, which ends up to be 1/3. that what you got, Mark?
Actually, no, I got 2 over 6. Square root of 9 is 3 plus 3.
Yeah, 2 over 6. Isn't that the same as a third?
Oh yeah, I was thinking. Yeah, I don't think I even simplified it. I think I just left it. You're right. 2 6 would be a third. This.
You're giving me a
Sorry.
heart attack. Oh my goodness.
Sorry.
Okay, no problem.
Yeah, but by the way, if you go back, if everyone wants to pause and go re-download the Dropbox has number 3 correct now.
Okay.
So that's, I was a little distracted trying to get that fixed.
Okay, so one thing that's true about both of these examples, and there might be a little different here, is that these functions were not defined at 3 or at -5, but their limits existed. And so these had a kind of a special kind of discontinuity. And the big thing about Unit 1 with limits is not necessarily doing all this algebra and evaluating limits, although it's not bad. It makes you better at algebra, obviously, but it's getting to the continuity and the definition of continuity, because if we know whether or not a function is continuous, we can make certain conclusions from that. So we need to, for ourselves, write down what it means if a function is continuous.
Are you intentionally skipping the one before this?
I don't know. What was the one before?
The horizontal asymptotes.
Oh, I did. Sorry.
That's okay.
Now I'm glad to see why we have 2 people here.
That's right.
Mark plus Verge equals 1 whole teacher at this
Between the 2 of us, we will get most of it right.
Okay. Sorry about that, but this is another use of limits besides talking about continuity. It says here on this one, find the horizontal asymptote or asymptotes of this function f of x is equal to the square root of 4x squared plus 7, all divided by 3x minus 5. Now, horizontal asymptotes are going to be really discussions or equations that are telling us about the end behavior, what's happening at the extremes. So this is really a question about what's happening to this function as x approaches infinity. So what's happening to the square root of 4x squared plus 7 divided by 3x minus 5 as x approaches infinity? That's going to be one of my possible asymptotes. And then maybe something else is happening as x approaches negative infinity. We'll take a look. So here in these kind of problems, I think to myself, well, as x gets really, really large, this -5 and this +7 is like sand on the beach. I mean, it's like, it's right. It's like, just like pixie dust, it doesn't really go to help understand what's happening at the end. But this square root of 4x squared is really, really important, as is this 3x. So in terms of the degree of the numerator and the degree of the denominator, you might say to yourself, well, I see a squared here and just an x here, so the degree of the numerator is higher. No, we're taking the square root of 4x squared. So essentially, as x goes to infinity, the square root of 4x squared is actually the absolute value of 2x. And then in the denominator, I have here 3x. So as x gets very, very large, this ratio right here actually becomes 2/3. You can even think of a numeric analysis here, like what happens when you plug in 100? What happens when you plug in 1,000?
Yeah. I always do things like when you're talking about grains of sand or whatever, is that, if X is like Bill Gates, like, and then we add $7 at the end.
Yeah, it didn't really change Bill Gates much at all.
So it's Bill Gates divided by, Mark Cuban. And if plus or minus $5, not going to matter.
Right. So when I'm saying like a numeric analysis, I'm thinking about like an input output here, 2 times 1,000 as x goes to infinity over 3 times 1,000. That ratio is still 2/3. So y equals 2/3 would be one of my horizontal asymptotes. And maybe that's my only one. I don't know. Let's see what's happening on the other side. A lot of times there's only one horizontal asymptote. But if there were, we probably wouldn't have picked it as an example. All right, so limit as x approaches negative infinity of the same expression here. Same idea as I'm going all the way out to negative infinity. Really what I'm considering is the absolute value of 2x, because that's the square root of 4x squared, and then divided by 3x. Numerically, what happens there at these very, very large negative values, or, you know, negative 1,000, negative 100, negative 222 million, I don't know. What's going on? Same thing, y equals 2/3.
Well, are you throwing in negative numbers?
I'm throwing in a negative for each of the x's. So I've got now 2 times negative 1,000, take the absolute value of that, get 2,000 in the numerator, over 3 times negative 1,000. That's just going to be negative 3,000. So to me, it's looking like my other my other asymptote is y equals negative 2/3.
Yeah, sounds right.
Sounds good?
I'm going to steal your screen for a sec.
Okay.
And just for anyone that wants the analytical and that absolute, because that absolute value of 2x, I know bothers some of my kids. I actually don't write this. I do it exactly how Verge showed it. But if you factor a 4x squared off of this, where I rewrite this as 28x squared over 4x squared or whatever, or I guess, I'm sorry, 28 over 4, then x squared over x squared. If you factor this off, this square root is going to approach 1. As this gets really big, that's going to get really small. So it's just 1 times that, and then the -5. And of course, we end up at the same place because math works.
Yes.
But for that analytical of like, well, how can I pull that part out and just leave the 7 behind? Well, because the 7 over stuff that you divided out is going to approach 0 and go away as x gets really large. It's going to approach going away. Never quite goes away, which is why we never get to the asymptote.
Yeah, that's excellent, Mark. I tend to be not as formal like that. Even though I dress formally, I'm wearing velvet today. That's how cold it is here. But I tend to be a little bit more informal as I approach math, and Mark tends to be a little bit more formal. So we definitely complement each other.
I was going to say, hopefully that works out, right?
Yeah, hopefully. All right, now tell me if I'm right now, Mark. We're going to talk about this.
You are where I am now.
Okay, so a function f is said to be continuous at x equals a if and only if only if 3 things are true happening here in this neighborhood of x equals a. First of all, f of a must be defined. F of a must exist. Okay. Secondly, the limit as x approaches a of f of x also must exist. We could call it L or something like that if we wanted to, or we might say, you know, exists. That would be okay too. What this means is that the limit from the left, the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x. These all exist and they equal that same result. And then finally, a function is said to be continuous if these two are equal to each other. If the limit as x approaches a of f of x equals f of a. If that's true, then the function is continuous at x equals a. Likewise, if f is continuous, then that will be true. That's what the if and only if means. It goes both ways.
And you'll see it used both ways quite often.
You know, one thing as we were preparing this lesson, I was thinking to myself, some teachers write the best study guides for their students, but who really needs to write a study guide for the student? The student. The student needs to write this stuff out for themselves many, many times, and to where they don't even have to look at it anymore, right, Mark? Like right. Mark's of the mind, like I want to write it so many times that I don't need it anymore to look at, and that's exactly correct.
Yeah, and even if you don't get to that point, you'll remember where it is on the study guide, which will make it a better study guide. And right before Verge draws this or takes us to the next thing, I'm going to steal again. because I just want to, I know this is a review. We're not reteaching everything.
That's why I'm
But-
going pretty fast. If
I
you've
know, but-
already watched us before, I'm going fast now because we're
Yeah.
reviewing, and I'm going
But
to
I
go
just
like my New York speed.
I just want to show the way I think of this to get all three parts, right? Is that this point has to exist. So that's our first bullet. The limit, so what we're approaching from the left, what we're approaching from the right, have to meet each other. So that's the first two bullets. But for continuity, those all have to line up.
You just want
So-
to use your erasable pen, right?
No, I just I think I like the graphic approach on remembering the three things, that it's boom, boom, and they have to hit each other. So
Absolutely. Okay, so so if they don't hit each other, I just dropped my little
You got-
paper on the floor.
uh-oh, you want to steal it back?
Yeah, I'm gonna get it back again. So if they don't, if a function's not continuous at x equals a, then we have different kinds of names that we might call it. And what Mark just drew, well, it didn't really remind me of that necessarily, but Mark drew all these earlier. But we have ways of identifying these different kinds of discontinuities. If the limit exists, but the function is not defined, it could be that this is the graph. Okay, the limit exists as you approach from the left and the right, but the function is not defined at x equals a. That would be considered a removable discontinuity. Would this one be a removable discontinuity? Does this one have a limit that exists? What do you think, Mark?
No, I think the left and right are not equal, so the limit does not exist.
Yeah, so
The
this is
left
that.
limit and the right limit, sorry.
Yeah, this is that jump discontinuity. And this would be in the category of non-removable. What about this one? Would that be a jump discontinuity?
Yeah, see, it does jump up and come back, right?
That's true.
But the first thing you said for the removables was the limit exists, right?
Yeah, the limit has to exist for the removal. So that's a nice example.
There's
of
a hole we can
removable.
fill in to fix it, right? We can
Mhm.
move the dot, or we can just color in the circle, and then it's removed.
What about this one? Does that seem like a jump, or maybe is it more of this category infinite?
I believe infinite is anytime there's a vertical asymptote from that's behavior from either side or both.
Okay. And this one is behavior definitely from one of the sides. So that being said, this last little card that we have in terms of continuity at x equals a, this would also have an infinite discontinuity at x equals a. Okay. Nice. So that being said, I'm going to do my very last problem before Mark does quite a few. And we hope we don't lose him this time, right, Mark?
That's right.
Friday, that was pretty exciting.
The slideshow is
excited.
closed, yes. I still think having the slideshow running in the background was what caused that disaster.
Okay, well, so in terms of continuity, these are some classic questions. It says here, find a value of q that will make g of x continuous. And then we've got g of x is this piecewise function, qx plus 3 for x is less than or equal to 1. And then x plus q quantity squared minus 10 for x is greater than 1. So we want to find a q value that will make this continuous, so that as we come from the left and as we come from the right, we get to the same y value. So we're not being asked to prove or justify anything here. I'm not going to go ahead and throw limits up there. I'm just going to think to myself, well, I want when x is equal to 1, I want this linear piece to be equal to this quadratic piece. That's where the issue is happening. This is linear, this top piece, it's very continuous. Quadratic, very continuous. It's at x equals 1 where the issue is. So I'm going to go ahead and substitute 1 in for x. So I have q times 1 plus 3 is equal to 1 for x on the quadratic piece, 1 plus q squared minus 10. Q times 1 is q. That looks like an 8. Oh my gosh. Hold on a second.
So the Q is my wife's fault.
Okay.
When I was writing these up last night, I kept saying, "Hey, pick a number." So she's like, I think there was a 43 at some point. She's like, "Is that too big?" I'm like, "No, it's fine." But the Q, she said Q, and it's like,
this is terrible. Okay. You know, you run out of letters pretty quickly though in math, you know, and some letters are definitely like, we never
reserved,
say, oh,
right?
why don't you pick the letter O? That would be good.
Yeah.
That doesn't happen.
Lowercase L.
Yeah. All right, so here we go. These are better, looking like a first grade Q, but it's okay. All right, so Q plus 3 is equal to, I need to expand this, 1 times 1 plus Q. I'm going to get 1 plus 2Q plus Q squared. Bring down the minus 10. And then I've got Q plus 3. And this is looking like quadratic. I'm probably going to need to factor. So I'm going to bring everything to one side. So let's see, subtract Q. Get my Q squared plus Q. And then 1 minus 10 is -9. And then minus 3 is -12. That's not too bad to factor. Q plus 4. Q minus 3. So my 2Q values would be Q equals -4 and Q equals +3. So true story, when I was doing this last night, working on what Mark had typed up, I actually made an error in here, factored really nicely. It factored great anyway. And then I went to check it and I started plugging in and doing a little mental math. I was like, this isn't working. So I think that's important to check the reasonableness of your answer. Both of these, if I plug back in, end up working. And you could make beautiful graphs on Desmos showing, you know, the line coming into the parabola and all that kind of stuff. And it really does work. But there are two solutions that work. I think in the interest of time, we might go to the next question, but I would encourage you to check those for yourselves and check them graphically as well on Desmos. Mark, you ready to steal my screen?
Yes, if we teach you nothing else, trust no one.
Trust no one. Not even yourself.
All right, so let me get this. I just rearranged my desk space a little bit, so I was racing against time. All right, so we just did this one, and that brings us to number 8, I believe.
Mm-hmm.
You can see 8 and 9 here, because 8's not going to take very long. But let's go ahead and get that sandwiched off. All right. So it says, given selected values of the continuous function h of x, what is the fewest number of times h of x is 43 on the interval from 0 to 30?
There's that 43.
Well, yep, there's the 43 by one. It says she, right after the Q, she gave me that. That's her Jersey number. All right, so we've got, looks like regular intervals here, 0, 5, 10, 15, 20, 25, 30.
Mm-hmm.
And h of x is 100, 40, then 40, then 110, followed by 30, 10, and 50. You know, so the fewest number of times, it could be 43. So what are we talking about here? So we go from 100 to 40, but what do we know about how we're going from 100 to 40?
We're going there in a continuous fashion. We are, right? I mean, it says continuous, so.
I just realized that my headset's not working, so you're probably seeing my chest. But
I can hear you just fine, though.
Yeah, but it's using the mic from the computer, and I think that's something that you were sounding like a fishbowl. That was what was my tip, because I've still got the muffs on.
Okay.
Sorry about that. All right, so I was like, why does it sound weird? I was like, I'm going to lose signal again. Oh no. So we're going from 100 to 40 in a continuous function, which means we're hitting every value or all of the intermediate values. Right? Looking at intermediate value theorem. And the conditions for intermediate value theorem are continuous function and looking for a value, 43, that's in between 140. So if I just want to say, where could 43s be? There could be a 43 right there. From 40 to 40, do I pass through 43?
Maybe, maybe not. We're not guaranteed.
That is the correct answer. Thank you. I asked, I just said, are we? I don't know, but must we? No. And then 40 to 110, then we're going to have to pass through 43 in if we take a continuous curve. From 110 to 30, we're going to pass through 43 again. From 30 to 10, we don't have to, but we might. We have no idea what's going on between these. It doesn't even have to be differentiable. There could be a zigzag going on, and we could hit 43 6 times in here, but nothing has to happen. So it looks like 1, and then 10 to 50, there's another one. So it looks like 4, because they did ask for the fewest, and I have to hit it at least 4. What's the most I could hit it? There is no answer.
So Mark brings up intermediate value theorem, the condition for which is continuity. So if you know that a function is continuous, you know that you can appeal to that intermediate value theorem. So anyway, there was no justifier or anything here, just had to answer how many times fewest number is 4.
So number 9, given that the limit of v of x as x approaches 7 is 6, and the limit of v of x as x approaches -7 is 3. And lastly, the limit c of x as x approaches 7 is 5. Verge, did you notice these were your initials?
Aww,
and that
so nice.
And that v of x and c of x are continuous.
You were really grasping like last night typing this up.
I just didn't want them all to be F and G.
Yeah.
And if you say that fast, it sounds a little risky. F and G again. All right. The limit is x approaches 7 from the right of v of the opposite of x minus 5 times c of x. So we're looking at limit properties, and we didn't discuss these at all today, but you had some properties, and a lot of them have to do with continuity or the limit existing. But because we're continuous, we know the limit exists everywhere, and if the limits exist, this gives us a lot of flexibility with these properties. Now, I know the limit's going to exist because these are two continuous functions. I'm combining them in various, arithmetic operations. So what do I know about the limit as x approaches 7 from the right? If the limit exists, Verge.
If you approach 7 from the right, or if you approach 7 from the left, it doesn't matter. If the limit exists, you're getting to the same spot.
Yeah.
I'm more curious about what's going on with that v of negative x.
That was totally superfluous. And then I can also break these up. So
yes,
I'm gonna
I
break
just did that on my paper.
and so I'm losing the plus, and I'm pulling the operators out. I'm talking with my hands, which is wonderful when you can't see me. This negative here, obviously, is just the subtraction. And then I can pull the constant out, because if I multiply a graph by 5, all I'm doing is stretching it at 5. So all the limits get moved proportionally. This one's really easy. Limit as x approaches 7 of c of x, they flat out gave me. And like Verge said, this is the one she was concerned about.
Mm-hmm.
This v of opposite of x. So x is approaching 7. So as x approaches 7, what is the opposite of x going to approach?
Are you asking me?
Yes, I am.
Okay, so that would be -7?
-7.
Mm-hmm.
So I'm really looking at, as this inside approaches -7, what does v approach? So that actually becomes that. And so the reason we can do this is we're looking at symmetry, right?
Or at least reflection.
Or at least a reflection, right?
Yeah.
We're plugging in 7, and then we say opposite. Well, the opposite's over here, and I've got this graph of v doing whatever it's doing, but I know it has a limit of 7, 6. It's continuous, so I know that's the actual function value. And it's 3 at -7. So I'm asking for the limit at 7, but then when I look at -7, I flip over here. So this is going to be 3 minus 25, or -22. And that is not a usual problem, but it is the kind of problem that's cool to stick on a test when you're not going to be able to Google the answer on the internet. Try typing that into Wolfram Alpha and see what you get.
And I might also say that we went through that really quickly right now, but I had never seen that question before last night when I was working it. And I thought about it for a while. It took me a while to figure out what was going on there. And I think that's an important challenge to take and think about it for a while and then come back to it and see if you understand it better.
Yeah, it's a cool problem.
Mm-hmm.
All right, number 10, I'm going to slow down on. We got 5 minutes left. This may be the last one we do. I think we may leave the others as your assignment / homework to discuss tomorrow for warm-up, possibly. I don't know if that seems like something you want to do, Verge, or if we just want to jump into unit 2.
Yeah, I mean, we could definitely, no, we can definitely put one of those on the warm-up, but there's also going to be something else in the shared folder that they can work on, that extra circuit that we put in there, but you'll talk about that later.
Yes, actually, it's not in there yet. I'm going to put it in immediately after because I don't want people working that instead of listening to us.
Oh, clever.
Yeah, I know. It's a teacher trick. You hand those out ahead of time. Some kids working on it in the corner, right?
Yep.
Okay, so we're looking at the limit. Is like in this one, you might try approaching properties. I know a lot of people have this one memorized, that, as a approaches 0, sine a over a
equals 1.
Yep.
I have it memorized.
Yes, you do. Or as b goes to infinity, sine b over b, which is 0.
Yep.
But this doesn't actually, you can make this a 1 over x squared, and you can do a little manipulation that's close, but it's not going to get you that exact sub. So there's some other strategies we can use. What I do know is, let's look at this actually isn't going to exist. But what's the limit as x approaches 0 of sine of 1 over x?
Well, it's got an oscillating discontinuity there.
Right.
But I believe that value is always in between 1 and -1.
Right.
I mean, yeah, because sine never goes higher than 1 or lower unless you have an amplitude change.
Yeah, 1 over x, right? If we're approaching 0, it's approaching infinity from the right, negative infinity from the left, and faster. So this sine wave is getting faster and faster and faster, but it's always bounded by 1 and -1. So we know it's hitting all of those values over and over again. But now I'm going to think about, what about x squared?
As x approaches 0?
Yeah, what if can I say this? I'm going to take the limit away for a second. And actually, I probably should have taken the limit away there. There is no limit. The limit doesn't exist, but the function is bounded. Thanks for the erasable pen.
No problem.
Been a big helper.
Might need to send some more.
I know, right? So I'm going to multiply this side by x squared, the interior, the middle, because this is a compound inequality equation, right? And the right side. And now, why don't the inequalities change? Normally we have to check for that when we start doing manipulating like this.
X squared is always positive, so you're not going to need to change inequalities.
Yeah, x squared is greater than or equal to 0, so we're good as far as that. And it actually doesn't equal 0 when we're talking about the limit. So we're allowed to do that. And now I'm going to take the limit of each part. And the limit of the opposite of x squared as x approaches 0. Well, that's a polynomial. And how do I evaluate limits of polynomials?
Just direct substitution, which, by the way, you did not do at the beginning of this problem, but I think you assumed that people kind of went ahead and plugged in and saw there was an issue.
Yeah. All right. And the limit of x squared as x approaches 0 is also 0 by direct substitution. Because they're continuous, we know the limit equals the value of the function. And polynomials are everywhere continuous. So now it looks like my limit is between 0 and 0.
It seems like it's getting squeezed.
Seems like the squeeze theorem.
I totally understand that so well, Mark, because you explained it. That's great.
Thanks. That's so sweet. Yeah. And if you do the drawing here, if we draw that graph real quick, we know y equals x squared looks like this. And the opposite of x squared looks like that. And then this limit that we're finding is this wave that's doing this, forever. Actually, I guess it wouldn't even do that. It'd be even tighter than that when it's not expanding. So what a horrible drawing. All right, try to do better on the other side. But if that's between 1 and -1, then it's just going to get squeezed right in between those two parabolas. And so that limit is 0.
Mm-hmm.
Also may have heard of that as the pincer theorem, sandwich theorem. I think one of our friends at Worcester College calls it the fly swatter. He'd heard it called the fly swatter because it gets flattened like that. And then there's another Scandinavian one called, was it Two Cops and a Drunk? And the idea is that if a drunk's walking down the street and a cop gets on either side of him and they walk towards the police station, guess where he goes.
Yeah.
And that's actually the official name in like 3 different languages. So we're not just making up stories. All right, it is 1:45. Problems that are left for you on this document is a tram problem, which it looks a lot like number 8 that we did with the intermediate value theorem. There is another table that has a calculator on it, which means you're going to have to do calculator active to evaluate some numbers there. A particle problem with a table, and then a compound inequality that we ask about continuity. So you're going to have to look at those 3 bullets of continuity, as well as figuring out how to show each of those is true. Along with that, there's a review circuit that is that's going to be in the Dropbox very soon. It's one I wrote. I do want to warn you, there's a calculator active one that's a table, and things like if you get an answer like 1 over the square root of 5, it is not in there as 1 over the square root of 5 because I wanted to make you have to look for them. I didn't want you to be able to work the circuit backwards. So you'll have to throw that into a calculator. You can type 1 over SQRT 5 into a search engine and the number will pop up for you so you can find those decimals. And there's also a factoring of 2 cubes in there that you might want to look at.
Right, but our exam this year is 100% calculator allowed. So definitely blow the dust off your calculator and use it some, between now and 4 weeks from tomorrow, because that's when the exam is, May 12th, 4 weeks from tomorrow.
Something like that.
Yeah.
And again, thanks for watching. Those are the links, and I'll put that one up last. Whoa, too late. That was a stop sign to warn me. If you have people that are looking for tech, there's still that site. And I said I was going to put this slide back up. I want to give you one last chance to get that schedule, because that is not the bit.ly that's in the description. The bit.ly that's in the description is to the whole folder. So.
Okay, tomorrow we'll be doing a review on derivatives. That's the entire unit, basically all the derivatives you need to know except those that require chain rule. So that will be tomorrow. I'm looking forward to it. We've got lots of good resources to share with you tomorrow, so we hope you can join us. Anything else, Mark?
No, I think we covered it.
Bye, everybody.